This is the first video of a 6-part series where I'll be going over the free response questions that were given on the 2021 AP Calculus AB tests. So here it is. I recommend that before we start, you go over all the questions first and try to solve them on your own. Hopefully that went well for you, so let's jump into part A. The density of a bacteria population in a circular Petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. Values of f of r for selected values of r are given in the table above, and then it gives us this table of values. Part A tells us to use the data in the table to estimate f prime of 2.25. Using correct units, interpret the meaning of your answer in the context of this problem. Okay, so let's just stick with this first part of this question here. It's asking us to find f prime when the input value is 2.25. So let's take a look at our input value, which is going to be r, or the radius. And if we take a look, we can see that 2.25 is going to fall right in between here, so in between 2 and 2.5. So let's just write that. And we know that in order to find, in order to estimate a slope, we're going to just have to use the slope equation, and that's going to be change in y over change in x. And to be particular, I'll write this out. F of, and here we're actually going to be using these four values to be clear. So it's going to be f of 2.5 minus f of 2 over 2.5 minus 2, and this is going to be 10 minus 6 over 0.5. And if we wanted to, we could actually just leave it like this. You will not get deducted points for not simplifying, but I'm just going to go ahead and do that, and this will turn out to 8. And our units are going to be, since we know that f of r is measured in milligrams per square centimeter, and we're finding f prime, we know that our units are going to be milligram per square centimeter per centimeter, right? And we can verify this because when we use the slope equation, we know that f of r is measured in milligrams per square centimeter, then divided by r is just going to be per centimeter, right? And for these units, I know you'll be tempted to just simplify this and say 8 milligrams per centimeter cubed. However, it would be much better just to leave it as this, because centimeter cubed would imply that we're dealing with a volume, whereas if we leave it as per square centimeter per centimeter, it's kind of implied that we're dealing with a rate as opposed to just a volume. So moving on to this next part, using correct units, interpret the meaning of your answer in the context of this problem. So like I said, the meaning of this problem is just going to be the rate, right? We know that right, our function is the bacteria population in our circular Petri dish with respect to this r. So if we find the slope of this, we know that what we get from here is going to be the rate at which that changes with respect to the distance. So if I write that out below, that's going to look something like this, where we talk about 8 milligrams per second per square centimeter per centimeter as a rate that's increasing, and we mention the density of the bacteria population, and we also say that this is true for when the distance from the center of the dish is 2.25 centimeters. So in these kinds of questions, as long as you use this kind of format, you will be fine. Alright, so hopefully that first problem wasn't too difficult. Of course, if you have any questions, you can leave them in the comments, or you can also just email me, and I'll leave my email in the description. So part B, the total mass in milligrams of bacteria in the Petri dish is given by the integral expression, this integral expression. Approximate the value of this integral using a right Riemann sum with the 4 subintervals indicated by the data in the table. So right away, I can see that we're dealing with a right Riemann sum. And whenever I see that we're using any Riemann sum problem and we're given a table, what I like to do is up here, I like to write the distances or the change in x of all of these values. And this just knocks out finding the width of each subinterval right away so that we don't have to include it in our long solution. So let me just write change in r just to be clear. So 0 to 1, that's going to be 1, and I'll write a box around it. 1 to 2, that's going to be 1 again. 2 to 2.5, 0.5. And then 2.5 to 4, which is going to be 1.5. So there we have all of the widths of the subintervals that we'll be working with. So then if we take a look at our actual integral, right? Our integral, which is r times f of r, we know that the height is going to be the height on the right of r times f of r. So the way we set this up, let's just first start off with this 2 pi. So 2 pi, open parenthesis, and as long as we get the first term, all the other terms should be pretty much the same thing. So as long as we get the first term out of the way, we should be good. So then we know that our width, we already determined that our first width is going to be 1. And the r and f of r values that we're dealing with, the height values, it's going to be on the right. So these will refer to these values. And let me just do that for everything else, just so that we're clear. Right, all of these widths are dealing with the heights to the right, since we know that we're dealing with a right Riemann sum. So 1, and we're dealing with an r of 1 and f of r of 2. So 1 times 2. And then from there, we can just do the same thing for all of these subintervals. So for our second one, we have 1 times 2 times 6. Then our third one is going to be 0.5 times 2.5 times 10. Then our final term is going to be 1.5 times 4 times 18. So let me just go back and label some of these just to make it more clear. These are the widths of the subintervals. And then these in blue are the heights. And since we know that it's a right Riemann sum, up here, again, we use the values on the right. So moving on, if we wanted to, we could actually just leave it unsimplified, and we could just give this as the answer. But I'm just going to go ahead again, and this is going to turn out to be 845.088. And no units are needed, so our answer, we can just leave it as that. So for part C, is the approximation found in part B an overestimate or underestimate of the total mass of bacteria in the Petri dish? Explain your reasoning. So when we're dealing with overestimates or underestimates, the first thing we need to deal with is whether whatever's in the integral is increasing or decreasing, and also whether we're using a left-hand or right-hand sum. So if we recall back to part B, we know that we're using a right-hand sum, and the integral that we were dealing with was 2 pi times the integral from 0 to 4 of r times f of r dr. So we're given that it's a right-hand sum, and the integral that we're dealing with, the inside, is going to be r times f of r. And we need to determine whether the inside of these things, the integral, right, is increasing or decreasing. And if we take a look up here at R and f of R, if we wanted to, we could actually just write out all of these products, or I could just tell that since R is listed as increasing and f of R is also increasing, then that by that logic, R times f of R must also be increasing. So we can write that it is an overestimate because we're using a right-hand sum, and R times f of R is increasing. So let me just quickly write that out. So here would be our answer. Overestimate, as we are using a right-hand sum, and R times f of R is increasing from 0 to 4. And it's always good to just be particular with these things, writing the domain here. If we take a look at the scoring guide, actually, the scoring guide tells us to, instead of just using the table to tell that this is increasing, what they did was they actually took the derivative of R times f of R, and they said that if you take a look at the scoring guide, you get 1 point for identifying the product rule, but this is not the case. As long as you determine one way or another that that R times f of R is increasing in this domain, then you are good to go, and you will score both points for this question. So for our final part, the density of bacteria in the Petri dish for 1 to 4 is modeled by the function g defined by this function. And we're asked, for what value of k from 1 to 4 is g of k equal to the average value of g of r on the interval 1 to 4? So it's asking us, in simpler terms, in the interval 1 to 4, when is the average value, when is this function going to be equal to the average value? So for this problem, I just start off by finding what the average value is. So let's just write g average is going to be equal to, and then I'm going to refer back to the average value formula of a function, and that's going to be 1 over b minus a, and we know that our bounds are 4 and 1, so 4 minus 1, then our integral symbol, then our bounds again, 4 minus 1, or sorry, 4 and 1, then our function of g of r. And if you're new to FRQ problems, if we have a defined function like g of r, there's no need to write out this entire section. We will still get points for writing out this average value formula if we write g of r. So g of r dr. And if we plug this into our calculator, we get that g average is going to equal, and actually it'd be more correct to write a squiggly equal, 9.875795. So then we have our average function of g right here. And from here, we set this equal to g of k and then solve for that k value. So g of k equals g average, which we found was this, and one way or another, we're going to plug that into a calculator, and we get that k is equal to, and actually squiggly equals again, k is equal to 2.497. So here is when this function is equal to the average value. And just some general tips for FRQs for Calc AB. Just writing definite integrals like these can score you points. In fact, on the scoring guide for this particular problem, just writing this definite integral, right, ignoring this part, just writing the definite integral scores you a point. And then another point is scored by identifying this average value function and how to solve it. And then the last point is received by just writing the answer. So again, let me repeat, just writing these basic things down, even if you might not know the problem, can sometimes score you points. Hopefully those problems went well. Again, I will link the scoring guide as well as a copy of the questions in the description. And our next video will be covering the second FRQ of this test.